Okay, thank you very much. I want to thank the organizing committee for the invitation. It's the first time we actually publicly talk about this very new project, the IBM Cortical Learning Center. For those of you who know Jeff Hawkins' work, you recognize the sketch on the right-hand side. You may be correct in assuming that HTM plays a major role in this project. So the team, the Cortical Learning Center core team, is listed here. It started in Almaden in California. The manager of the team is Veni Mino, who is here. But it now has spread to the East Coast, and there are some other people involved, particularly on the hardware side, which I didn't mention here. By the way, we always like to welcome visitors in Almaden. So if you're in the area, don't hesitate to stop by. With some prior warning, please. So the talk, which is relatively non-technical, will talk about why we are doing this, technical focus area, the applications, and then about the hardware, which is a significant part of the project. And time permitting, I'll talk about a completely different project going on in my organization in Almaden. So, as the name says, the Cortical Learning Center is about learning. To put in perspective the other two older, well-known projects in IBM research, Watson, as you probably all know, is more a traditional AI system which has a really fancy database and a sophisticated search engine. But it's doing very good things, but the problem with it is that it requires lots of human work. Synapse isn't about learning really, as we all know. It's about energy efficient execution of something which has been learned elsewhere. So why did we pick HTM as the driving model behind it? When I first became aware of it by reading Jeff's book on intelligence years ago, what struck me, that was the first time I saw somebody attempting to create really a system level view of how the neocortex work. So much work in neuroscience has been such pinpoint studies rather than trying to get a holistic view. And half of the team, myself included, are physicists. We like this concept of keeping things as simple as possible, but not simpler. The old joke about physicists is if you ask a physicist to increase the milk production of cows, he'll start with a spherical cow in a vacuum. So there's some proof to that. HTM, of course, it's all about learning, unsupervised and online learning, just as we want to do in this area. And it's an example of machine intelligence, not machine learning. But another area which I found really intriguing is that it seems to hit the sweet spot in biological fidelity. It's not so simple as overly simplified as a point neuron, and not so complicated like some of work done in Lausanne, that there is little chance to ever build a large-scale model with extremely complex high-fidelity neurons. Specifically, one area which feature I found really interesting is the fact that the primary learning in HTM is not by changing weights, but by creating new connections. And many, many years ago, maybe in the late 80s, long before I was even interested in the field, I happened to read a paper about two rats which came from the same litter. One of the rats was put in a training, went to Stanford, so to say. And the other rat had led a very boring life. And when microtome slices of the brain were shown, and it was an absolutely dramatic difference. You could see how few connections were in the rat who led a boring life, and how many were in the same in the rat which went, quote unquote, to Stanford. So this is clearly important. So the model is happy learning still, but it does not use spikes, the spike time independent plasticity. Also the use of active dendrites I think is really important, because if you think about the implications of having a one-level input device with, say, 10,000 inputs. You think about it, it makes little sense to have that. I don't want to go into details. Another area is it's a very universal model. And the biggest problem nearly we have in IBM with neural stuff is if you constantly need people to tune it and whittle with it, you cannot scale it up to large business. So that is a really important feature. After Jeff's talk, you don't really need to go into detail, but the basic idea is you have a hierarchy. At the bottom, you have sensors. You form representations which get more and more stable and invariant as you go up the hierarchy. At the top, you have outputs which could be recognition, could be predictions in time, motor commands. Motor commands are fed back, very important part of the whole theory. More reasons why I picked HTM. Like in physics, you are usually winning when you pick a good coordinate system for your problem. Here, picking good data representations is absolutely crucial. And the powerful property of the sparse distributed representations underlying all the HTM work, I think, is really a big catch here. Another area is PIME is not an afterthought. It's a first-class citizen HTM. It has very few parameters. Very important, all saying if you have enough parameters you can fit an elephant. That's not happening here. Complexity is captured in hierarchies. This means the same building block can be used in multiple levels of the hierarchy, which is good. On cautionary notes, however, it is likely that for a long time purpose-built machine learning application tools, maybe better numerical accuracy for specific tasks, but you have to keep changing them, which is a big drawback. And the second one is some industries like do not want self-learning systems. Examples are the automotive industry or medical device industry. In fact, the latter are forbidden from having learning systems by the FDA. But we see a really big potential in HTM, both for near-term applications and for the long-term, how does the brain work kind of research. So we do have formal, I think we're working, nice collaboration with Jeff and Nomenda. We are only about an hour's drive apart from each other. Now, IBM, our funding model is such that a big chunk comes from, for long-term research from headquarters, but an even bigger chunk we need to raise money ourselves for monetizing with external companies or government. So some initial applications which we see here and actually in most cases working on are Nomenda has already demonstrated the power of this approach to anomaly detection. We're looking at crop analysis from Lancet A data. Citrus screening is a big problem in Florida, and we have a big chemistry department in Almaden, and it's one of the projects where it's the chemistry of that. So being able to detect that from Lancet A, from satellite is important. Subvocal voice analysis. We have lots of turbo pumps in the labs, so it's easy to predict failures with HTM. Longer term opportunities are a lot of what we are interested in is text analytics. The Cortical IO, which is an Austin firm using the HTM, the SDR representations, has shown that there are really wonderful things you can do with it. Another way to do text analytics is to use the temporal aspect of HTM, where you describe text as a temporal sequence of words. An area which should be very interesting is anomaly detection for cybersecurity. Such events are anomalous, hopefully. But this has been a little bit hard simply because the cybersecurity guys have forming an actual new division in IBM, so we are pretty busy with that right now. We have brought new projects in the Internet of Things, particularly vertical sensor data fusion, source and dialog predictions, and possibly also automating streams. Streams is a product in IBM where data, to analyze streaming data, obviously, but it is in some sense all manual. A data scientist takes pre-configured building blocks which do something and arranges them in a flow chart, and when in goes the stream and out comes something useful. And this chart, which is actually a couple of years old, shows actual applications today of streams. The problem is, again, however, whenever the world changes, somebody has to sit down and change the model. So automating this would be really useful. Just a short, I will try to be concise in terminology going forward. Layers, levels, regions, and HGM building blocks. Layers are the cell layers in the brain, neocortex. Levels are logical concepts, like these levels here. Regions are really the physical implementations of level in the brain, but they tend to be sideways shifted, because the neocortex is too thin to stack them vertically. And then we have the HGM building blocks, which are 3 of them are used in each level, which is the spatial pooler, the sequence memory, and the temporal pooler. So we are working on refining this, implementing it actually in our own software for all kinds of, not necessarily technical reasons. What we really haven't done yet is to demonstrate really the entire hierarchies of the levels. A major area of work is now sensory motor mechanism. The layer 4 function in the cortex. More about this in a moment. I had that originally planned to show a whole bunch of videos, but testing the time, it doesn't quite work. So let me show a very old video, which some of you have seen, but I find it easy to explain. Let's see. Okay. And impressive. This is a program which Wayne wrote about a year ago, was the first internal implementation of HTM. Please look only at this panel here. What it is the input, it's a single level HTM model. It gets fed with a temporal sequence which is chaotic in time, as it looks really crazy. It's not random, but there's some hidden structure in there. An HTM which has not seen it before is seeing it now and tries to predict 4 time steps in advance what is going to come. So the blue is the input, and a little bit ahead there will be red dots. Initially, because it's the first time HTM has seen it, it will not try to predict, and then after a while it will start doing that. This is all real time on a laptop. So this blue here is the input. And here the prediction of HTM, so far none. Now it starts to predict. The red dots I had, see, of the blue curve. It's getting the hang of it. As you have missed some. But they're pretty impressive in that we saw that, realized there is a pony here. I did a little test trying to show myself this slide and trying to predict it. And HTM was noticeably better when I could do it myself. Okay, here is a view inside the actual network doing that. It is a single level. It has columns of 16 neurons stacked in mini columns, but for visualization purpose, each column is squashed into a little 4x4 array. So this is really one column. And the colors encode whether the column is active red or whether a neural cell or neuron in there is in the predictive state. Let's just run. Oops. No. That's how it looks with the model thinking. Those of you have seen this amazing picture of a zebrafish where neuron activity is made visible. It looks amazingly similar. Okay, this has to do with diagnostics. So on applications, we have really 2 different types of applications. One, let's call it research applications for deeper understanding of the brain. The other one for the applications for monetizing, which we need to do in the near term. Let me talk about the research application, saccadic vision. We're happy to say that Jan Hammerström is going to fund part of his work here. So this is, up here in this audience, I don't need to explain what saccadic vision is, but it's interesting how tightly it's coupled really to higher level tasks in the brain. So people are asked different questions against this picture, the saccadic vision, measured saccadic paths are very different. So why is an interesting research application? Well, for one, I love a challenge. This really is a challenge. But it's a good vehicle to demonstrate motor sensory integration. It exploits and introduces time into vision, which should make it the extension from static images to videos relatively straightforward, which is important for some applications. And we have reasons to believe, and I hope that will become clear in a moment, that it's more resource effective than, say, deep neural networks, and hopefully also less brittle. So this area is really, there's a whole bunch of different flavors of saccadic vision. The first one would be to simply test the integration of the motor sensor. Before we are getting a little bit more ambitious here, hopefully not too ambitious, to actually do object recognition. Eventually one could do a visual Turing test, but that's not something we're really actually working on. So let me describe the algorithm a bit. So take a pretty large pool of images, say 100,000. And out of each image, we'll pick a number of patches, hopefully in an interesting way. So we have a total pool of in the order of 10 million patches. And out of these, extract a library in the order of 1,000 salient features, which are designed, constructed in such a way that all the 100,000 images, or I'm sorry, all the 10 million patches can be reasonably well reconstructed by selecting a subset of these special salient features and superimposing them. So here's an image space with all kinds of patches in there, and here is an extraction of the salient features. This will look a little bit like Gabor plots. And so say this particular patch, which looks like a tire, might be constructed by selecting these ones highlighted here. So this is another video, but it's now greatly accelerated and running on a whole GPU system which we built for that, which shows the actual extraction of patches, of these millions of patches. It's hard to find a point at the right place here. Yeah, come on. Should have moved it a little bit. Yeah, it's not funny. Suck. Should have practiced that before. Higher when it starts to. Well, I'll show it as a separate file in a moment. I know return. Leave the presentation mode. Yeah, let's try this. Yeah, okay. Now it's working. No, it didn't really run. It's static, it doesn't change. Anyhow, for a few effect. And I'll go back. So here's proof of a pudding. So here is a random collection of input patches. And this is after it has been reconstructed from using this in the order of 1,000 salient features. So you can see it's not perfect, but it gets the gist quite well. Okay? So the next step then is the object recognition is the combination of two things in saccadic vision. You have a path, like here with two airplanes, and you have description, so you combine the description of a path as an STR with description of each patch in the sparse way I described a moment again. And when you put it into time where each different patch corresponds to a different time. And so the idea is you combine the combination of patch location and patch description in HTM sequence memory, which represents when one instance of an object and multiple objects then go into the temporal pool. I must say that part is to be done. This is not demonstrated yet. So a few words about hardware projects at the Cortical Learning Center. First, a bit about philosophy. The purpose of this project is really learning, not energy efficient execution. And I personally feel it's way too early to cast learning algorithms into specialized silicon, let alone post-silicon devices. And conventional languages are a really good way to test ideas and concepts and algorithms. Another reason for us to do it's relatively conventional hardware is the fact that, as pointed out before, a key feature of HTM is that learning is the changing of the topology. How do you do that in hardware? That's not easy. So it's much easier if you describe the topology and the synapse state as big tables in very big memory. You have some half-baked, no, that's too kind, it's not even half-baked, that's what quarter-baked ideas how one could might such learning topologies, but don't want to go there yet for quite some while. So I strongly feel that the best way to have platform and scalable platforms for the development is optimized highly parallel for Neumann machines. I was starting to make a list what one should do, but when I came across a presentation which Dan gave last year, and it's a perfect description, I think, what should be done, with perhaps the exception of this new topology which we need, i.e. with today's HPC processors are unnecessarily complex, don't need high precision floating point, we don't need deep caches. But what we really do need is much better communication, much better access to memory by having many small, relatively simple devices. So that's where we're going after. Now, for a moment you will be very unhappy because what I think the way to do is, what we're actually working on, is to combine Wavescale and 3D stacking to create lots of communications, hardware, and lots of memory. Now, whenever anyone says Wavescale, the first reaction is, are you crazy? Wavescale has always failed. But this time, I think it's really different because the inherent resilience of HTM. Jeff was reporting yesterday about that like half of the neurons can be killed and it continues to work. We have done some similar situations. This is one of the team members in Yorktown Heights. This is a version of HTM. This here is time, and this here is some output. The higher the bar, the better the output is. I don't want to go in detail. I don't even remember exactly what it was. But the black bars are when the results, when all 100% of the neurons are working. The thin hashed bars are after 50% of the neurons have been killed at this point. There's some latency, so it doesn't go down immediately. So it goes down, but it then crawls back up, pretty much the same level. The coarse-grained hash marks bars are when 75% of the network has been killed. Now you see a considerable dent in the performance, but it crawls back out. Something strange happened here, I don't know what happened there. So this is why we hope that, quite certain actually, that there is a good way to build such systems in Wavescale. So the architecture, for IP reasons, I don't want to get into details yet, but it will be n pairs of 300 millimeter wafers vertically stacked. Each pair contains two components, one wafer which has an array of pretty simple processors, possibly IBM's embedded DRAM as caches, and combined with a DRAM wafer in which is mostly storing the tables of synaptic states, about half a terabyte per wafer of DRAM. One thing, by the way, to point out is, as we analyzed it in detail, one really has to watch out about the addressing scheme because the data types are really small, like 8 bits for the synaptic state. The if you have a large system and you want to be scalable, you have to be really clever and try to minimize the number of bits used by address space. Vertical communication is through densely spaced vias. We have actually very high density. We don't even need it all. And horizontal communication happens when onto the logic wave on the AND side. The power dissipation will be limiting the N. We think that we can cool in the order of a few kilowatts. And this whole thing is fortunately kind of doing that IBM is doing that anyhow for other applications, so we can somewhat coattail on this. I should admit that at this stage of this project, I am not particularly concerned about power. It's more important to get the algorithms and logic right than getting too hung up about power initially. I know that's probably pretty controversial, this statement, but it is. That's kind of how it looks in cross-section. Now, it would be crazy to charge off immediately into the building this right away, so we're building a pretty large FPGA system, which is the same architecture, 1,000 nodes, a terabyte of RAM. And it's a dual purpose, as a platform to develop a detailed architecture of a Wavescale system, but also to give us more horsepower for HTM simulations sometime, first half of 2016. We need it for the psychotic work. Now I do have a request to a neuroscientist community. One of the most critical things in the detailed architecture of the systems is to know more about the spatial distributions function of neuron communication. Lots of things depend on that, really. So what it would be nice to have would be maybe a three-dimensional plot where this axis is the distance between two neurons, between the somas. Here's how often they talk, and how many neurons fall in that. So it would be a density distribution of neurons with that features. I've looked at the light search, I couldn't find anything really describing that. So now to the context switch. In spite of what I just said about the right thing for HDM is to stick to pretty conventional but optimized neuron system. I have a couple of people in the organization which have been liking to build devices. We have been working on phase change memory for years and built a pretty medium size, actually pretty large neural network, not based on silicon. I want to spend a couple of minutes on this at least. This talk was given, the presentation at the International Electron Devices meetings in December, and a reporter from Register was there, and he afterwards published this article, which cost quite a bit of chuckling. So the person who is driving that is Jeffrey Burrs, one of the people in Wayne's organization. So in this system, which is reasonably large on the scale of most of these non-silicon networks which have been built, it has 165,000 synapses. Now, phase change memory is quite asymmetric. You can gradually increase the weight or the conductivity, but you can only turn it in one fell swoop down. So each synapse is then implemented as a pair of phase change memories as a voltage divider, so you can go in both directions. Now this is not trying to use HDM at this point. The idea was, the purpose of the project was to figure out what the device properties are. So it is really conservative in the choice of both the choice of the algorithm, backpropagation, and the test set, MNIST. The accuracy achieved was 82.9%, not great compared to silicon-based ones, but it shows it does work. The summary was that the network itself very resilient to random effects like device variability, stochastic effects, and so on, but very sensitive to gradient effects which steer all the devices into one direction. So here's one of the presentation, one slides that shows here as a training. This is based on the extracted parameters from the actual hardware simulation. If anything is linear, unbounded, it learns more and more, great. But in the worst case, where you have a linear, nearly worst case, we have linear bounded asymmetric system. Training actually makes it worse because it pushes you into one corner of one particular plot. So hopefully, by the way, these results do not devalue what I said earlier about the robustness of HTM against failure, because in software these kind of things do not occur. Yeah, this is training. Okay, that's it. Thanks. And questions?
Thank you for that. This is really an exciting project, and
Thank you.
I was interested to see that you use Wavescale integration, which we have worked on, as you know, for a while. And I was surprised when you say that on your AND wafer, horizontal communication bandwidth is not the limitation. That's what you said, right? So then what is your argument for Wavescale integration?
Oh, we could put even more on. It's limited by the, it is the following trade-off where I don't really know the answer is. What should be the ratio, how much memory should be assigned for each processor, the AND? And how much memory bandwidth does the processor have? And the communications bandwidth, which we can achieve horizontally as well as vertically on this system, is probably going to be higher than the total bandwidth, the aggregate bandwidth the processors can accept if the limit of the number of processors is determined by the amount of memory which you have. So that's the trade-off. That's how that came about.
Did you simulate that? You have some kind of an executable system specification where you can...
With spreadsheet simulation.
Spreadsheet simulation, because that's a good start.
I'm a big believer why we're doing spreadsheets or build the system, not to get too clever in the middle.
Any further questions for Winfried?
Okay.
Oh, we got one last quick question.
So I was intrigued by your discussion of eye movements as
of
eye movements,
yeah.
saccadic eye movements. So certainly one of the things that's always been pointed to as a solution for is a focus of attention.
Yeah.
But another thing that it does is actually introduces at contrast boundaries. It introduces a very highly correlated signal that is actually a very easy thing for a neural network to see. And it's very consistent also with the idea that these sort of correlated signals pull out aspects of a scene that are important, like boundaries and like locations in three-dimensional space. So I actually would applaud that direction. I think it's a richer direction perhaps than even you guys realize yet.
Very good. Thank you for this comment. Okay.
Okay. Well, thank you very much.